the talk title is called The Art and Benefits of Computing Eventfully. I've kind of deliberately made this title a little bit more of an open kind of talk rather than saying that, okay, this is how you do things, kind of like that. The goal is that, I think we live in this world. It's full of so many exciting things, and sometimes we tend to maybe just want to seek, the way of mechanically how to solve problems. And so it's always good, I think, to step back a little bit, look at what things are, look at it from a different angle, kind of more like an art of something. And then also understanding, having that art, the reason for that being more of an art than a science. To me, I think they all, art and science should kind of all come together and create something beautiful that should also be very purposeful and solve some problems too, or even if it's not solving, giving us some kind of aesthetic kind of satisfaction, so to speak. And then that's how I look at it. So anyway, without kind of going into all of these details, it's just more of a discussion, really looking at what things are available to help us to do computing, like in an eventful way. Okay, so I won't get into all the details, but I'm developer advocate at the DataStax, and I'm currently a developer advocate there, and for the company that's really data focused type of company, and I'm with the streaming team. So I've been working on event streaming for the company for about a year, a little over a year. So I kind of find myself always thinking in terms of events, right? How do we solve problems using the event approach? So that's why I feel it's good to create a talk that's kind of centered around this, and it's kind of more from an artistic point of view and beneficial way too. So I'm based in Chicago. I'm also the president of the Chicago Java Users Group, and I'm also a community builder. I'm a Java champion, and also I am, previously I was in engineering and doing development for over 20 years too. So I'm kind of, like, I understand, right? Most of you are developers coming in and looking at things, and I find that that's what it is, right? As a developer, I started off, and you feel like you're only focusing on solving problems only in a small area, so to speak, and you go very deep. But the thing is, it's good to look at things from a breadth kind of point of view and see what's out there. So that's what I like to do. Anyway, so that's me. And this is just another pictorial representation of me from my company. That's the slide deck, and that's what I work on, and already described, so I won't go into details. And with that, let me kind of step through then for the agenda for today. It's more like I feel like, is doing computing is kind of doing things the eventful way. And in today's world too, when we're really living in a business world, we're kind of driven a lot by marketing. There are like so many different terms that comes out, that fly out, and it can be confusing. So my attempt too is to kind of collect all of these terms that are relating to computing. And it's computing that's event related to events, I should say. So these are what I've come up with. Maybe you can come up with more terms too, but essentially, right, like event streaming, that kind of involves pub-sub approach or message queuing type of approach. And then event processing, that's kind of interesting. It's more like after you get the data, you need to process and then kind of do complex event processing to make sense out of it, to derive more value out of it. And that's event processing. And then if you go down to some fundamental level, it's basically, I call it more fundamental, meaning that it's really dealing with the message exchange, right? The data, you're kind of exchanging data, transferring data from one point to the other. But there's event-driven versus message-driven approach. And then there's also that event-driven architecture. It's more on an architecture level. How do you design system that kind of takes on that approach, which is not exactly like what I talked about earlier, streaming and processing. This is more of an architecture level. And then there's also event sourcing, right? Event sourcing too is more about, I'll get into it a little bit. So event sourcing, and it's kind of more supporting the modern day of computing. Event computing is event sourcing. And then event storming is dealing more with requirements gathering, which is kind of interesting. When I first heard of the term event storming, I thought, well, it's some way of doing things in which you are still doing events, but in the computing. But it's not quite on computing. It's more of a higher level thinking of brainstorming on the requirements gathering phase. So that's event storming. And then there's also microservices. Okay, so we can't escape that, right? It's everywhere too. It's kind of stateless versus stateful type of microservices that kind of leverage on the event approach, right? And then serverless apps too is very often too. It's also using event-driven type of approach. That those are serverless apps. And then also then another aspect of computing, I think is also find it fascinating. And I kind of seems like I spent some time to kind of really think through, how is it related? Reactive systems, reactive programming, how is it related to events? And I actually did also a talk for the Reactive Summit too. It was more of a keynote, a small keynote, and I was kind of comparing the two. And I kind of walked through some kind of thinking process and realizing they are very close, I think, if reactive systems and reactive programming, very close to kind of all of this eventing that we're talking about. But it's kind of a branch of its own, shall I say, kind of like that. So I'll touch upon that a little. And then I'll kind of move more into essentially to look at the changes of the data, the requirements, what is driving this change for more eventful computing. Understand some fundamental states of data too, and essentially event computing is really dealing more with data in motion, right? There are data traveling from one point to the other. Fundamental states of data, and then really we then examine into the benefits, right? Why do we want to do things this way? And then there's a bit of resources too, and I'll share with you at DataStax what we have in terms of streaming product too. So that's the discussion for today. Okay, so I'm going to start now. There are many facets of computing events. Again, this one, I talked some of these things already in my previous session, so please bear with me if you've already heard it. First of all, when we talk about events, right, what exactly is it, right? We need to try to understand it, because I think when we all first doing computers, learn to program. Usually too, it's like when people said, oh, you work with computers when you're little. You say, oh, computers. And first thing people would think is learn to program. That kind of seems to be very basic and fundamental things we need to work on. However, I'm kind of thinking that the way we teach computer science for young children to start, it's good because we sort of have used a simplified version. We basically look at our many-faceted world, and in fact, it's kind of a very eventful world, in fact, right? And rather than, or how can I say, it's more like, okay, if we look into sorry if I'm jumping around, it's kind of late in the day. Sometimes I kind of not thinking it's so right. So anyway, what I'm trying to say is that first, okay, let's take a look then in what is an event first, right? Event, to me, fundamentally, it means something that just happens, right? It can be a life event of a baby is born is an event, a musical event, and we go to a concert, or going to a conference like this is an event, right? All of these are events. But notice that the event happens and it's immutable. You can't change it. And it represents some sort of data. But like on a complex event like this, of course, you have many data. We have people, we have events, we have schedule, all of these things. And that's kind of fundamental, is what event is. Now, kind of looking further as scientists, if I look into event and interpret it in terms of using theory of relativity in a scientific way, is basically a point in time. So each event happened in a point in time, and that's what I think when it gets to computing is we're trying to capture is basically the data that occurs in a specific point in time. So that's what event is. Okay, that's very fundamental, and like I said, I feel kind of going back to my earlier talking about, well, when we first starting to learn about computers, we actually never was taught about thinking in the event way, because it's just harder to think of. How do you teach someone to say, okay, something happens is abstract, you have to think in terms of something happens in time, and it's harder. So therefore, we kind of flatten everything, and then we're learning to program, doing programming in a very synchronous way. And we might say, want to program some variables that represent some data, some variables, and then we'll say, okay, let, some formula like doing multiplication, A, equals 1 times 10 or something, right? And then you store the data. And in the meantime, too, you are submitting the request. The request will get processed synchronously because you send a request over to some processor and it processes and you wait for the answers to come back. That's kind of how we learn, how to do computing, rather than thinking of computing in an eventful way in which, things can happen. It can happen at any time. And the question, you submit a request and the request doesn't get answered till later. That type of stuff can happen in real time, right? And that's what the challenge of doing computing is, in a very intuitive way. I think it's just harder to do. And now we're trying to do it that way because it makes more sense and also really is imitate the real life scenario. We need to do fraud detection. Those require eventful type of computing that you can look at real-time data and react to it essentially. Or like using AI systems, you're looking at a set of data, you immediately look at the data and be able to interpret what it is and give some kind of analysis, and essentially analysis comes out with some very useful data that you can look at it right away, that type of stuff. So that's kind of more like the event kind of way of looking at things. Okay, I hope it makes sense. Okay, then now this one is just another kind of representation. I call it an alphabet soup of event computing. It's more kind of artful way, but it's already, I talk about it in the agenda. All of these terms, right, that is kind of thrown together. But fundamentally, too, again, we're looking at the data that we need to deal with. And that's kind of what you call it, like, events can be many things happening, but ultimately, too, we're interested in the data. The data is what brings value. Or in some cases, too, data can come. It doesn't immediately becomes apparent. So you have to do some processing, and then basically it's called derived data that comes in that would give you more value like that. So, but again, I already repeated all of the terms, so I won't kind of go over all of it, but we can kind of talk through some of them maybe. Yeah. So again, right, I kind of stepped through maybe just for clarity purpose, right? Let's talk about it. There's event sourcing. I find it interesting. How many of you are already working with event sourcing, perhaps? Like the CQRS, like, what is it? Often command query responsibility segregation pattern. Yeah, so it's, yeah, exactly. Yeah, thank you. Yeah, this gentleman here is so, thank you for being so responsive too. So it's basically, what it is that, traditionally when we're doing computers, we're using database, let's say, right, we store a table of information. You may be storing the state. Only, at that point in time, you kind of say some status is an order can be open, and then it goes into processing or pending, all of these things, right? So you only keep track of the state at that time, at the most current time. However, for event sourcing is that in order to do event computing a bit more accurately is that you want to store the data at all given points in time. So that's what the techniques we're using in here is described as event sourcing. So basically, you can think of all of the events that I described earlier occurs in point in time. They are immutable. All of them get stored. So maybe like, your time, like in seconds, it could be, first second, second, all of these points of data get stored in your database. And then the benefits of such is that you can always go back to doing replay. Especially too for companies such as, I've worked at a trading company in Chicago, the Mercantile Exchange. There are lots of data, but you want to be able to trace back because trading can happen real fast, but you want to store every point, whenever mouse click, doing something, the state of your order changes. You want to keep that data every single point in time. So then anything that happens that is wrong, you want to be able to go back to your event sourcing table to replay the data. So you maybe go back in time. Yesterday at 3 o'clock, between 3 and 3:15, you want to replay, then you can pinpoint what goes wrong. Because otherwise, if you store just one state, then there's no way you go back in time and figure out what happens at 3:15. Because what you're storing is already next day, 3:15, you can't go back. Kind of like that, right? So that's kind of event sourcing in kind of a nutshell about what it is. So that's that. And then again, want to look into event storming. It's about when you start a project and then you want to bring in like all of the stakeholders to come together and kind of define some requirements. As you know, and I'm sure all of you have done projects that you are working with your customers, but it can be internal company customers, could be working on an accounting system that involves your project management, the accounting, all of these things, and then all of you come together and basically brainstorming idea, and then that's kind of described as event storming. You're kind of coming together, define the functional requirements of the system, and then you come together is event storming. So it's less of a direct computing, it's more of the event requirement gathering phase. But then as we get more into like event-driven architecture, it's basically an architecture that takes on an event-driven approach. So everything that, that will change the state of data is being triggered by some events that can happen. So you have to basically understand what is going to affect your system, what kind of changes. You have to anticipate all of these and basically use that approach to drive the architecture, essentially. Like it's an event-driven architecture. Okay, and then there's also then the techniques of event stream messaging, which I talked about earlier. Messaging is basically dealing with, you want to have data, you want to send data from point A to point B, for example, or just sending data. It can be pops up, can be just, I emit messages, and then only interested subscribers will subscribe to the messages. Those are kind of messaging. Those are more techniques. You can use publish, subscribe, as I just described. And then pops up to the advantage of it is that because the sender doesn't need to worry about the address of the receiver. You just send out the messages. I don't worry about it. I let the broker deal with it or some kind of middle agent. So I basically send out the messages and I label it. It can be called a channel. In microprofile, it's called channel. Or in PubSub, Kafka, Pulsar is called a topic, right? And JMS is a topic or something. You essentially send your messages to the topics and the broker will handle delivering the messages for you. So that's kind of more like a PubSub approach. It's more determined, how to do something is determined by the vendor or a library that determines how to implement it. But the fundamental concepts, it's there. And then there's also message queue, in which you have messages that are sent from point A to point B, but you do need to know where you send to, maybe to a queue, where the receiver will pick up the messages from the queue. Once it's picked up, then the messages will be gone, like that. So that's message queue. It's more dealing with really fundamental sending part. Now, for event streaming, which I also talked about earlier, is basically dealing with all the events happening at any given point in time asynchronously all over the place. But all of the events come together, a series of events. That's streaming. You're like a whole bunch of them that can happen at any time. And so it's kind of a challenging thing, but then at the same time, it's so fundamental to today's computing because it allows you to have the data, to get the data immediate and be processed immediately. It's a real-time, has this real-time kind of capability to it, is event streaming. But it leverages on event messaging techniques like pops up and message queuing. So, okay. And then we get into like event processing. That's interesting too because you might have also be working with, for example, Apache projects, because these are Apache Pulsar. That's what I'm working on now is Apache. Then there's also like Apache Spark, right? That's kind of used widely by machine learning, or like Apache Beam. And then there's also lately, there's Apache Flink. And Flink is like for event processing. So Flink too doesn't ingest the data, but maybe it relies on Kafka to ingest the data, or Pulsar comes in, and then I can do Flink is further analysis of all of these data. Another kind of interesting event kind of or real-time analysis software in Apache is called Apache Pinot. Pinot is also doing analysis, and that's actually driving LinkedIn, like all of the LinkedIn feed, right? As you can see, like you'll be on your LinkedIn profile. All of a sudden, it tells you how many people have viewed your profile. That type is real time, being done in real time, and that's done by Apache Pinot project too. So, for example, Apache Pinot can rely on Pulsar, and I've done a talk too on Pulsar. You can have Pulsar directly feed the data in. Immediately, Pinot will do all of the analysis, and then there's a company called StarTree. It's actually based in the U.S., but they also are the ones that kind of immediately process the data, and you can then see all your feed, like live feed, very accurately in real time too. So that's more about event processing. Okay, and then, yeah, then all of that I've touched upon already. Then there are microservices, and then microservices as such deals more with also an abstract kind of layer of concept. And it's not like how you do it, but it's kind of abstract level too, as you know. So, and can be stateful or stateless, and then getting into reactive systems too. Reactive is a little different to me. I find the more I understand it in my mind is more higher level, so to speak. It's kind of like it defines in abstract term what it should be. Your system should be like reactive systems is that you need to have systems that are highly responsive. So that leverage on event kind of messaging way of doing things, that you can have very responsive type of scenario, ingest high volumes of data and respond back quickly, right? So that's reactive systems, the responsiveness, the scalability side of things too, especially if you use PubSub type of way of doing things. You can have, PubSub, for example, like Pulsar, you can actually send 1 million messages in a second too, like that, because it doesn't need to worry about address. It just shoots out all the messages, so it's real fast. And so reactive systems. And then there's also, what else? We have scalability, responsiveness, and recoverability. So if anything goes wrong, you always make sure that another node will come up and cover that too. That's reactive systems. And also messages have to be very message driven in nature too. So that's reactive systems. So anyway, so these are kind of just describing all of the different aspects of event computing in here. Okay, let me kind of go further. Okay, I think I already talked about this. Is also from my previous talk, the event streaming processing. Streaming is basically describe ongoing delivery of these events, right? And also too, I pointed out too, for example, like packages or libraries like Apache Pulsar, Apache Kafka, it's only mostly too, they are only for processing streaming data, not for media streaming, and that's different. These days, I know we watch movies, live streaming of this Netflix, for example. These are streaming too. They are also data happens in high speed. The difference is that for media and audio, they do need certain amount like synchronous processing, because all of the data, they all comes in data frames over the wire. They all need to be reassembled in the right order. Otherwise, you'll be watching or listening to a music that would be all out of sync, right? So anyway, I just want to point out Apache Pulsar is more for data streaming, kind of rather than media streaming. So, okay. And then complex event processing. This actually has to do with, after it deals with a series of steps. You first ingest all of your data. It's basically event ingestion using Kafka or Pulsar. Then it capture all of this data and then analyze these streams of data as they arrive in real time. And then you want to identify some opportunities, for example, fraud detection system at a bank, right? You want to make sure all of your accounts being monitored closely, that there are no suspicious events happening. Or if there's anything that's suspicious, you want to immediately notify the account owner that, let's say I live in Chicago, but then I notice that I'm debiting money in Bangalore, then they might say, well, why are you doing this? Is this really you, right? That type of kind of systems are really complex event processing. Many things are going on, monitoring things for you at the same time and notify you immediately if something goes wrong. Or there can be retail systems like order processing, retail, e-commerce. Those two can immediately analyze your keystroke. You're doing some things on the website, and it will identify you. You are trying to buy something, buying like a chair, buying some furniture. All of a sudden, and then they might say, oh, you're buying this chair. I have different brands of chair, and I will suggest to you. That also can be done immediately. That can also be, you can be using that techniques in like artificial intelligence, machine learning type of systems that you immediately kind of analyze all your data and draw really accurate kind of predictions, recommendations for you in real time. So those are complex event processing. Okay. And then here, I already talked about event-driven versus message-driven. And then the streaming for PubSub too, just wanting to point out to streaming, again, relies on the PubSub way of doing things, relying essentially on a broker to receive all of the messages, and then subscriber will subscribe to the messages to a topic. And they will only receive messages if you subscribe to it. And that's why it's very fast and high speed and very scalable. And then another one, techniques we use, semantics we have is this queuing. The queuing is more about one-to-one. You have a queue you kind of first in, first out. So messages arrives at the queue, and basically receiver will pick up the messages as it comes. After it's picked up, then it will be removed from the queue like that. So that's also like for very efficient and decoupling the sender and the receiver. So these are like more like this, techniques. Okay, and then when we get into talking too about event approach, if we are not using the event approaches, basically the older ways of doing things are batch processing. Maybe, I'm sure some of you have worked with batch systems, and they actually are still very useful too, because even, let's say you are dealing with some of the, event kind of driven type of systems, you might still want to do a certain level of batch, like kind of mini batching too, like let's say what pops up or IoT systems. Because you may want to collect all your data let's say in a device, and the device maybe want to batch up the data and send it to, let's say in a field, you have IoT devices collecting the data, then you want to batch them up and send them in small chunks, and that will eliminate too much of an overhead of sending things over the wire, each individually too. But anyway, going back to here, event approach versus batch processing. What we used to do things is more of the batch way, in which we're collecting all of the changes that happens during the day. And basically for some of the systems that are less critical, systems of record, like employee systems, you have employee data update. You want to collect, those are not urgent. So you want to collect all of these changes and then group them together, send them in one batch jobs over to your server in another region of the country, whatever, and then process it. And those has its own place in computing kind of space too, because you want to process those things offline a little bit kind of more in bulk, and it has to be done, but not urgent like that. So it's batch processing. Okay. Now, then let me kind of get into a bit of the fundamental states of data just a little bit, and just want to remind folks too, sometimes when we're doing event processing, I find that then we may not be thinking of this. The fact is that let's understand too, we have, for event computing, it's really relevant for processing data, right? So there are three states of data, fundamentally. It can be data at rest, which is like, in a database or store, some kind of storage, right? It can be database, some kind of cloud storage at rest. And then there's also data in motion, is when you are streaming and data is moving, like doing messaging, passing from one point to the other, data in motion. And that's what the eventing mostly are dealing with for data in motion. And then there's also data in use. I think then that would be more of the processing kind of part. Okay, here. So basically now the next part is just talking about the benefits of this event approach in computing. But first too, let's take a look at some traditional ways of kind of our system, right, before we get into what it should be. So look at this, right? It's just kind of all together, and that actually represents a monolith systems that we're more used to. Monoliths are basically one systems, and you handle everything over there. But as we know that sometimes doing things in a monolith system is easier, because you don't need to have to do as much like network kind of communication between different processes. All of your processes may be within the same area, the same cluster, whatever you want to call it, right? Server, and everything is there. However, the thing is that it doesn't scale as well. What if your system, you need additional servers, additional nodes, and that's why too now we're moving more to kind of breaking things up into smaller pieces, and then also have cloud system clustering kind of system too. So now then also, then if we kind of look a bit then further, besides the monolith systems, it's basically looking into data. And there's also used to be data pipelines that are actually being done using the ETL, the old way, extract, transform, load, right? These are, kind of like the older ways in which you are getting data in batch, kind of you extract them, and then basically after extracting, your pipeline will send it to some transformation process, right? And then it loads it, after it has been transformed, you load it into some kind of storage. Now, the drawback with such an approach is that the old ETL system is that it's slow. Everything also tends to be in a synchronous way of doing things, right? You processing everything in batch, and then when it's all done processing, then you move it to processing, and then all of these things, right? And it can be network bandwidth can also be huge too if you're dealing with large sets of data, the ETL process. But that's why too, in general, ETL processes are more associated with larger batch kind of processing that happens during offline. But it's just more expensive too, and process itself tends to be heavy. And if you need, some data immediately, you have to wait too. You can't, any changes that happens, you can't get it immediately, as we all know. And it's expensive and tends to be, these software were developed by bigger corporations, right? Like maybe IBM has these ETL process or Oracle, all these things, and they are quite expensive. And they also have like a proprietary way of how do you interact with the system. So you need some specialized skills to do that. It's not open source of these things. So essentially, it's just not able to keep up with the time. So these are like old ways of handling of the data. Now, looking at the demands of this modern digital world, and so when we talk about modern system, what is the definition, clear definition in today's world is basically, it's kind of resemble of what I talked about earlier for reactive systems too. But first of all too, we are usually, in today's world, is referring to cloud native systems. These are really, essentially are running in cloud, and they have to operate in a very, kind of native way that's kind of native to the cloud. And as we all know, cloud native tends to be, dealing with smaller pieces of software, or smaller pieces of software components. So very often, too, we'll be making use of microservices to help us to do things, right? And all of these things. And then the overall effect of such is that we want systems to be highly responsive. You want to be very fast. Requests being sent over to your, to your system. You need to have very immediate, kind of almost immediate or close to real-time type of response. Also very scalable. The system needs to be able to handle the load in a very dynamic way. More requests coming in, you want to have enough processor to process it. And then if your system is idle, you want to immediately not use the resources, especially in a cloud system in which you get charged by the minute, right? Things like that. So very scalable, very resilient like that. And resiliency really is dealing with systems that needs to be able to recover and kind of bounce back if something goes wrong. You need immediately to be, maybe another replacement node needs to come up or like needs to be immediately fixed or something, right? That you don't block the rest of the systems from running. It's very resilient. And fundamentally too, if you kind of look at it, what we're looking for is really real time. Everything has to happen like right away, immediate, kind of like that. So these are kind of requirements of the modern system. And then when we're talking about real-time systems, that also kind of has to do with transmitting too on the more fundamental level is with the data. It needs to be transferred as messages. And these are the requirements we need to look at too. A bit of a, kind of lower level is looking at this is you want the data to be basically the reliability and resiliency aspect. So that relies on system that needs to be able to guarantee the delivery. Earlier, too, I talked about our Apache Pulsar system, too. It has built-in guaranteed delivery. Like messages get sent, once you are in the broker, sent to the broker is get acknowledged, your data frame, that messages will be recognized in the system. And even if a node goes away, something goes away, when it bounces back to it, it knows that, okay, you have a messages waiting to be sent. So that type of built-in capability is very important, that quality of service as well. Like are the messages being delivered once only or deliver more than once or at least once? All of these are kind of clearly defined too. So that's kind of dealing with transmitting of the data as messages, right? And it has to be very responsive. So as a result, we're kind of using a synchronous way of doing things. It's no longer synchronous. It gets sent. And then, but the difficulty is that with asynchronous style of processing is that it gets harder when you try to do any tracing or debugging. If something goes wrong, it tends to be harder to trace too, as we all know. But then with today's system, for example, you can also set up observability type of capability into your system to help you with diagnosis too, that type of stuff. But I just want to point out responsiveness also comes with a kind of price too. You need to make sure it can be tracked, right, if something goes wrong. And also too, you want to make sure your system being responsive is very lightweight and all of the components needs to be loosely coupled, meaning that the sender and the receiver should not be tightly coupled. You send the messages and somebody else will deliver it and making sure someone is receiving it like that. And then also scalability can be achieved by using pub-sub type of mechanism. Also, another thing is basically dealing with the message ordering too. In some cases, right, you want to make sure messages gets delivered, the packets maybe needs to be ordered in the order, ordered properly in the order as it is being sent, that type of stuff. So these are kind of some concerns that you need to be aware of if you're dealing with transmitting data as messages in the modern times especially. So now we can look at some new ways of handling data. So just wanted to kind of point out too, these are like microservices architectures, basically today's standard. And again, we're kind of looking at a bit of a picture, looking at, used to be monolith, like all of these different things, the components all run together in one chunk, but now we're breaking them up individually as individual components kind of isolated from one another. There's plus and minuses too, because then in this case too, if you have microservices, even though, yeah, everybody's running microservices, but we don't think of the fact that they are all individual, and because they are all independent, then it requires communication between them. And so it's actually not as easy to do. And also it can also come with a price in terms of performance too. I was just, actually now I don't have exact stats, but I know that I talked with Kirk Pepperdine, who's a kind of a very kind of experienced person in performance at Oracle and with the JVM. Oh, actually now he's at Microsoft now. But he was doing some tests too with microservices and testing JVM responses, but he did say that it's actually because of, you have each microservices, each has its own resources, maybe a database or something, then actually there's a lot of I/O that's involved to each individually. So it can increase the performance too. So it's, the thing is, yeah, we talk about microservices, but the idea is that you have to design your system so that you want to still minimize all of these extra I/O that may not be needed, things like that. So just something to be aware of too when you're designing your microservices. But again, just wanting to point out to this new way of handling data. And this one too is basically also describing all of these different components as messaging. Is basically you can also leverage on some messaging middleware that handles each individual too for transporting of messages as well. So, and okay, so this one too, I just thought it's just maybe interesting too. A lot of times though, if we're looking at our systems today, right, basically it's the consumers that set some expectations of the solutions that you're going to be taking, right? From a customer's perspective, they're looking at it from a user experience kind of point of view. But then, maybe like leaders, right, of a decision maker might look at SLAs, right? These are service level agreements, all of these things. They're looking at cost and is it, kind of, make sense, the cost and justify what you're trying to do. But like we have different levels of processing things, and on the developer, on our level too, we may want to have different options of doing different things, all of these things. But it's kind of, each layer seems to operate individually, but they all should be working together in concert with one another. That's why I thought this might be interesting to show you this slide. And also to the bottom layer, for example, like developers are dealing more with the application layer, but there are also like operators or more the DBA, what used to be traditional database admin, or these days are called platform engineering folks in the cloud platforms. And so they are probably dealing more with the infrastructural side of things too. So they also have to think of that too. So I'm just showing this to kind of show what it looks like, right? The picture of what we're working with. You may be only focusing on the developer level and not so much of the layer below, but the fact is everything needs to kind of all work together in concert with one another is what I'm trying to explain. So, okay. And this one too, just kind of a jump, I know I talked about microservices, but then we look into modern day, right? The way to solve problems. We can be using event streaming. And then event streaming too, let's kind of compare with the time when we're not streaming, right? Kind of going back to over here. The old days was maybe like not exactly like streaming. Over here, not streaming is basically more like an ETL type of approach, is that you extract the data, you ingest the data, and then you persist it. Persist is you want to write it to some kind of storage, maybe a database, a file systems of some kind, and persisting it first, and then from there, then you kind of cleanse the data. Coming back, you need to do selection, extract the data again, and then process it, and then persist it again, and then select it, so on and so forth. As you can see too, like doing things the older way tends to be taking a bit longer because it involves the the part of persisting the data, kind of writing to disk and then reading from disk, that always involve extra time. Even though you think, oh well, each thing might take 0.1 of a nanosecond or something, but you get so much data, then it makes it not worth doing it the old way. But the new way is basically streaming. We're dealing with modern day ingesting data as it happens when it comes, and immediately in memory, you're processing the data without writing it to disk. So it naturally is faster too. And then after you process it too, you also can basically write it to a sink. That's what we kind of identify as, as a data pipeline. You have a source of ingesting data, process it in memory, then output it to a sink and immediately. And so it tends to be always faster too in this case. So these are just like new ways to kind of think of how to process data. Okay, I think then pretty much that's all I have. And again, just wanting, kind of summarizing, right, and sharing some of the resources. I just want to kind of have this talk more like, let's think about, right, there's computing, doing computing in an eventful way. And also, too, because I'm talking here, as a person from DataStax, so we have solutions, too, that are making use of Pulsar. That's an event streaming platform. And if you're interested in that, I didn't touch on Pulsar at this talk because I already did it. But if you're interested too, I'm always there too. And if you want to look up the information, these are the open source link, on Apache.org, the Apache Foundation, Pulsar. Pulsar makes use of Bookkeeper too to manage all of the log messages if you're interested in that. And also makes use of Zookeeper to manage all of the cluster data, the multi-tenant kind of data too. And then the rest too are all of the DataStax information. And actually, if you're interested, if you want to stay behind, I can also show you if you want to try out our Astra streaming platform. That's the managed cloud that's running, Cassandra, the data at rest. And then also we have data in motion, which is our Pulsar too. So I'll quickly show it to you. But otherwise, there's also Astra Streaming, which is the managed cloud. And then Lunar Streaming is if you want to deploy it to your own cloud, write your own Helm chart, all of these things, but manage yourself kind of in your private cloud. But we have support for you too. Or you can also run it completely open source Pulsar as well. And then also, if you're interested in more about Astra, there's a capability called Change Data Capture too. That's CDC for Astra. That's only like capturing data changes in Cassandra at this point. So just thought I'd share with you too, all of the resources. And then if you are interested in working, trying out our DataStax, the Astra platform, if you are, let's say, you want more credit, right? If you are a business owner, you want to develop using our technology, we'll be happy to help you as well. And also we have a booth here, a DataStax booth. If you haven't visited us yet, we're kind of up a little bit. I don't know the exact location, but up a little bit, you'll find our DataStax booth. And today's t-shirts have run out, but if you want t-shirts, come early tomorrow, we'll have more t-shirts. So I know that that's always kind of welcome by folks. So again, the point is that we are just always here to help you too. Yeah, and it's not just we're selling things or something, but we're here, we're really open source people too. And okay, and then another thing is I also have a Twitch stream if you're interested, if you're like live streaming, live coding. So that's where I kind of do more demos too in there. But usually I do it on Wednesday, and I think the time 2 p.m. might be kind of late for you. But the thing is it gets saved too, this, if you can watch, and I can try to run some like earlier streams too if you want to watch it live too. Let me know. So that's my Twitch TV link. And then with that, I want to thank you, and also want to point out to you, if you want to stay in touch, I have a Discord server too. So it's my personal Discord over here. So you're welcome to join, and then send me any messages, or if you have ideas you want to talk about, I'm always open to ideas too, and I just love talking to folks and meeting folks like yourself. So thank you very much. I hope it is helpful, and yeah, please stay in touch. Yeah, thank you. Yeah.